Okay, so we have now an example problem that deals with fabrication. Let's take a look at the problem. The problem says that a process uses a 20 centimeter diameter wafer and a 52.3 millimeter squared, check the units. The ingot's $6,000 and can be sliced into 30 wafers. The process results in 0.03 defects per millimeter squared. So make sure that we note units here. There's 20 centimeter diameter. Diameter is also important to note. And then the defects and the die size are given in millimeters squared. Also note that this says millimeters squared. This is millimeters squared. We're going to use a centimeters in order to find an area, so we're going to have to do some unit conversions there. So what do they ask us? Well, they ask then, how much does a wafer cost? What's the yield? How many dies fit on a wafer? What's the cost per die? All right, when we ask how much does a wafer cost, remember that we have an ingot and we have a wafer. The ingot's like the tube, and then the wafer is what's sliced off from the tube. So remember that an ingot, although they come kind of like a helium tube, eventually cut off the ends, and it's a cylinder. And then with this ingot cylinder, we slice off the wafers, and those wafers are sliced. So we can get 30 wafers from this, and we're going to slice that ingot into 30 wafers. So how much does it cost? Well, the wafer costs $6,000, and then we get 30 wafers in it. And so then with that, we get $6,000 and we get 30 wafers. And with that, then the cost of the wafer is going to be $200 per wafer. What is the yield? Well, this one, we're going to go and calculate it using a fresh sheet of paper. We remember then, if I can get that into frame, those are the criteria. What we'll need to know then is we'll need to know the area of the die, and we'll need to know the defects per area. And the yield is given to us. This is an empirical formula, and the yield is always going to be 1 over quantity squared, 1 plus, and the notes expand this out, but I will abbreviate it area of the die and the defects per area. Area of the die, defects per area divided by 2, and this is a quantity squared. And one of the biggest things that people miss is this square. So then this is going to be equal to, running out of graphite here today, it's going to be equal to 1 over the quantity 1 plus the area of the die is 52.3 millimeters squared, and the defects are 0.03 defects per millimeter squared. So this is millimeter squared, this is millimeter squared. We can get those directly. And then remember the square. And with that, then when we do that calculation, we end up getting 0.314, but yield is usually expressed as a percentage, so that's 31.4%. Next, we're asked how many dies fit on a wafer. The number of dies per wafer. Well, this is a very rough approximation, but we assume the wafer has a certain area. That's going to be pi r squared. And then we're going to be putting all these little dies on it. And so how many? It's a terrible approximation, but we're going to take the area of the die, so that's how many square millimeters, how many square centimeters this is, divided by the area of the circle. So the area of the wafer is equal to pi r squared. But remember, it gave it to us that it was a 20 centimeter diameter. So this is going to be pi times 10 centimeters squared and that's going to be 314 square centimeters for the wafer area. And the die area is given in millimeters squared. I'm switching to a pen. Die area is 52.3 millimeters squared, but that's equal to 0.523 centimeters squared. Millimeters squared, centimeters squared, we need to move that decimal place twice. So the number of dies per wafer is going to be 314 divided by 0.523, that's centimeters squared, and then we get 600. All right, we get 600.4 if we do the math. Yes, I understand you can't have 0.4 of a die, but you know what? This is an ugly enough approximation anyway. We could toss it out, 16.4, even the 600. We're not going to get a total of 600 because we're going to get fringe effects. We're going to use that approximation and understand that if the die size is small compared to the area of the wafer, it's going to be close enough. Okay, the last thing is the cost per good die. And the problem didn't specify that it was a good die. Well, we could have just gotten that, we try to make 600 of them, but we really care about how much good dies cost. We're really only getting about a third of them. We try to make 100, we're only going to get 31 of them that we can sell. So the cost per good die is going to be, let's first find out the number of good dies. Number of good dies is equal to the number we tried to make, 600. I'll just leave it at 600. And then the yield, and that is going to be equal to 188.5. Now this does make sense. That 0.5 does make sense because this is a percentage. On average, we get a yield of 0.314. So this decimal place actually makes sense. But the wafer cost is $200. And at the end of the day, we only get 188.5. We tried to make 600 of them, but most of them were waste. So we only got 108. We paid $200 for the wafer, and so then, drum roll please, we get $1.06 per good die. So that's the dollars per good die.